Okay, following on from pressure at depth, there's a video in here somewhere about that. The next topic is forces on submerged surfaces, and I've gone down the route of like a dam or a sluice gate. So some of this stuff theory was used if you watch the Dam Busters. I'm assuming you've all watched the Dam Busters. If you haven't watched the Dam Busters, I suggest you stop the video now, go and watch the Dam Busters, watch it 8 times, and then come back and watch this video. Or there is a couple of good programs with Richard Hammond. I think it's the ones out now. I think it's called Big, and there's one about a massive dam in Holland somewhere, or Germany. But it goes through all the pressure that this water puts on a wall. So obviously we're not going to be building dams, and we're not going to be dropping bombs on dams, but some of this theory does apply to that. So forces on submerged surfaces. So this is meant to be like a dam, and this is meant to be water. So here's our water behind this dam. And obviously that water puts a force on that dam, obviously. So all this pressure and all this water has a force on this wall of this dam. This here is the height or the depth of water. So depending on how much water we've got behind it. And this is the breadth or the width or the length of the dam wall. And F stands for the force due to the water. So all this water here is applying a force on this dam wall. If it's too big, obviously it's going to go that way, and it'd probably create a moment about this point and knock the dam wall over. This force does act at a certain point called the center of pressure, which if you have watched the Dam Busters, the bouncing bomb came along, the ones that got past everything skipped along, sank, and at a certain pressure, certain depth, exploded, because that's where, at that point, is where most of the force acts, and that's called the center of pressure, which we'll see in a bit. It has got another funny word for it. I'm sure you'll laugh at that. Anyway, back to this. So F is the force due to the water. A is the area, so it's going to be the area of the water. So it's going to be that sort of area in there, which is that height times by that length. Density of water, obviously if you've got oil behind here, you've got water, so that depends on the density. And this thing called Y dash really is, it's density, gravity, area, and so it's the average force really. So all Y dash is just H divided by 2, which whatever that H there is, halfway down. So the force, right, we're working out there the force halfway, or the average force between that height and that height. That's why we're doing divided by 2. So it's not the force there. Obviously there's more force. There's going to be, let me put that up. Because of where we are, there's more force here, isn't there, than there is there. You'd have thought, because you've got more water. Okay, there is a point where the maximum pressure is, but for now, the force on the wall due to that water is F equals density, gravity, the area times by this Y dash, which is just the height divided by 2. Now, following on from that, obviously measured in newtons. Following on from that, this force will cause a moment. So depending on how you do it, that force there will cause a moment either about that point, going by my diagram it would, or we could have some sort of gate and it's hinged up here, and you can have a moment about that point. So depending on how you're doing it, this force will create a moment about a certain point. So obviously that force there perhaps will create a moment trying to tip this dam wall over like that. Or if it was a gate, you could have a hinge there and it will try and turn the gate that way. Because you could have a sluice gate, or you could have a gate to regulate flow, or a hatch. So depending on what the situation is. But the moment is, we know that moment is force times distance. In our case, we're going to use this thing called H dash, which really is the center of pressure, and that is where that force tends to act. It acts at the center of pressure, which is also called the G spot. Don't laugh, but it is. So at a certain depth, and it's not halfway, it's about 2/3 down here, that's where the center of pressure is, which is what this H dash is. This H dash is this thing called the depth where the force acts. It can be called the G spot, always makes you laugh, or the center of pressure. And Barnes Wallace on the dam busters, that's where he wanted the bombs to bounce along, sink to a certain depth, certain pressure, and explode. So that the center of pressure is where a lot of the force is. So that's where most damage would have occurred with the dams. So this center of pressure is simply 2/3 the depth, and D is the depth of water. Okay, or H on this diagram. Don't confuse it with H dash. H and D, right? So 2 times D over 3, or 2/3 of the depth, would give you this center of pressure. So if you wanted to work out the moment from the top, that's what you would use, because that H dash is coming down like that. That is what the H dash is telling you. It's right. So if you wanted to work out from the bottom, you could take away H from H dash, would give you the distance to the bomb. So you can use this formula to work out moments depending on which point you're going to go from. On the examples coming up, I'm going to go probably from here most of the time. But when I'm saying H dash, it's just 2/3 of the depth, and we're going to be using the force, which is the force we used here, times by that H dash. Obviously, moment is measured in newtons per meter, and it's got a clockwise or anti-clockwise, so depending on which way the force is. So basically, after all of that, that's the two formulas we'd be using in the next examples. So here's an example. We've got a dam wall, depth of 6 meters behind it, 6 meters of water. The wall is 12 meters long. Calculate the force on the wall and the moment about the base. The base is all about the base. So it's that point there is the moment about this point, not this point. So we're going to go from this point here. The density of water is 1,000 for now. So there's my little diagram. 6 meters of water. The wall is 12 meters long. Density of water is 1,000. We need to work out this force, where it's acting, and the moment produced by that force about this base. So we need to find force and moment. So first of all, we'll find force. There's a formula, just as we did up top. This formula here. Diggy. That one there. So F, density, gravity, area, and Y dash. Don't forget, area is just 6 times by 12. So it's the area, it's that area there, look, in there. Obviously, the deeper the water and longer the wall, the more force you've got, the more area you've got, more pressure you've got. So 6 times by 12 is 72. square meters. Make sure everything's in meters, correct? And this y dash is just h divided by 2, or that's the same as h divided by 2, which really is half of that, isn't it? So our height of water is 6. 6 divided by 2 is 3, when I last looked anyway. So the force, right, the average force, right, because we're doing the average height really, and it's like halfway. Density is 1000, gravity is 9.81, the area is 72, and y dash is 3. So whack that in your Dewberry, times by 9.81 times by 72 times by 3. Thank you very much. So all of that, you can put that in, or you can press ENG, 2.11 meganewton. So that's how much force is on that wall. Now the next thing we need to work out is what moment that force. So here's my dam. It's got a force here. Right, and here's my depth of water, say. So that force there is going to create a moment about this point, because there's the pivot, there's the force. That's all we're doing, force times distance. We know that this force acts at a certain depth down, which is this bit here, this pressure, center of pressure, which is 2 times the depth divided by 3. Now the depth of water is 6. So 2 times by 6 equals that, obviously. Divide that by 3. So 4. So this force acts 4 meters down. To go up here. So it's the top of the water, and this force acts 4 meters down. That's the center pressure. That's where most of the pressure is. As simple as that, or well, we've assumed a lot of things here, but 2d over 3. So the force is there 4 meters down, center pressure. Obviously, the depth of water is 6, so from there to there is 4, which means from there to the base is 2, and we need to do the moment about the base. So moment is force times distance. There's the force, which is this. The distance to that, the pivot point, the base is 2. So all of that times by 2. So 2.119 times 10 to the 6 times by 2. 4283, press ENG, 4.238 meganewtons per meter. That's how much of a moment, obviously that moment is trying to go that way. So it's an anti-clockwise moment trying to push that dam over. So we've worked out a force, and then we've worked out the pressure at depth. We've assumed that that force acts at that pressure of depth, that center of pressure. And that's the moment that force that we've assumed acts there would try and tip this over. So just using the two formula, that one and this one, and just making sure that we work out the correct distances. Obviously, if say there was a hinge bit there, this was a sluice gate, then you probably use that 4 meters, because the force would be 4 meters down, say. So number 2, same thing again, not to scale, obviously. I was trying to be clever and do a bit of perspective, but it didn't sort of work out. So dam wall is shown below. It has water, 20 meters depth of water. Let's go blue because it's water. The wall is 60 meters long. What's the force again? And what is the moment about the base? About the base, all about the base again. So this is very similar to the last one. Density of water is 120, 1020. So 60 meters long wall, 20 meters behind it. Work out the force, and then we'll work out where it acts, and then do the moment. So just like before, that's the formula. So that's my density of water, which is 1020. This is my gravity, 9.81. Here's my area, that's the area. 20, depth times by breadth, 60. 6 2 to 12. And 2 knots, so that gives me an area of 1,200 square meters. This y dash that we'll use, so we're saying that this force on average, because we're assuming things here, we're not working out the force exactly at certain places, but so from that point to that point, we'll go here, say, so the amount of force there is going to be h over 2, which is 10. So we know density, we know gravity, we know area, and we know this y dash. That gives a number for force, and we're going to assume that force acts at the center of pressure, which is going to be 2d over 3. So first of all, look at the force, 1020 makes a difference. Gravity is 9.81. 1,200 for the area, and times that by 10 for the y dash gives me a force of all of that. Okay, you can put that in, but don't miss out the noughts, or you can just press E and G. 120 meganewtons of force. So that's how much force that water is pushing on that wall at that distance, really. So that's the force, and now we go to the moment about the base. Don't forget about the base. So we can use this formula. It's just force times distance. Don't forget. We're just trying to work out now where the center of pressure is and where it's likely to break, and the most amount of force would be at that center of pressure. So we're going to work out this distance here. So there's my force we just worked out. Okay, we'll say it's going to act h dash down, which is this center of pressure, 2 times the depth over 3. We've got 20 meters of water behind it, so 2 times 20, divide that by 3, 13.33333333. So I've gone there. So from here to here is 13.33, and because we need to do the moment about the base, we need to work out this distance here, because force times distance. So we know is 20 meters from there, so this is 20 meters, and we know from here to here is 13.3, so from here to here has got to be 20 take away 13.33. I've stuck just the 2 3s there, 6.67. So this distance here from the base up to where the force would be acting, the center of pressure, is 6.67 meters. So that's the force times the distance I'm going to use for the moment. So there's my force, and there's my distance. There's my force, there's my distance. Force, distance. The force is 120 meganewtons, and the distance here to the base is 6.67. So force times distance, that's all I'm doing. 120 power 6 times by 6.67. Press equals. All of that, don't write all of that in. You can if you want to, but you may get a few noughts missing, or may add a few noughts on. Press that, 800 mega. Moment about the base is 800 meganewtons per meter. That's how much of a moment going that way. So you could even say anti-clockwise, because obviously that's the moment that being produced at that point. So which means that this here, whatever this here, this dam has got to produce, to remain standing, it's got to produce a moment going the opposite way right, and a force going the opposite way to stop this thing from going, which is what the dam busters did. If you haven't watched that film, go and watch it. Number 3, same type of thing. I got a sluice gate, which is just a gate. Required to keep water from exiting the dam. The depth of water in the dam is 5 meters. So we've got 5 meters here. 5 meters. And the gate is 1.5 meters wide, so 1.5 here. If the density of the water is 120, 1020, calculate the force that the gate needs to provide. I've used the word provide, not a very good word to use, but force that the gate needs to provide to keep the water in. So we need to work out this force here, really. So we know this force here is pushing that way. This gate has got to provide a force to go in that way, equal and opposite, really. So it's the same as the last question, just I've introduced direction now, really. Size and direction, so it's the same formula, just we'll work out this force here first. So that force is going that way, which I'll call negative, or to the left. So this sluice gate, whatever it is built out of, has got to have a force equal and opposite to counteract that same force, but going plus, which I've said to the right. And then the same thing for the moment about the bottom of the gate, in order to stop the gate being pivoted by the force of water. So this force here, like we've done before, creates a moment about this point, trying to tip it anti-clockwise. Whatever this sluice gate is made out of, the force this way has got to be equal and opposite to this, and the moment has got to be equal and opposite to that moment for it to stay up. Obviously, if that moment is bigger than this moment, it's going to collapse in on itself. So all we're doing really is working out these numbers and then just saying equal and opposite. Because that moment is going anti-clockwise, this moment, to balance it, has got to be going clockwise. So I'm calling clockwise positive and anti-clockwise negative. I'm calling to the right positive and to the left negative. It's up to you. You can go the other way as long as you stick the same notation. So the force on gate due to the water, it's the same formula. Density of water, gravity, area is going to be 5 times by 1.5. So 5 times by 1.5 gives you 7.5. That's the area, just like we've done before. And we put a number in for this y dash, which is the height of water divided by 2. So the height of water is 5, or the depth of water is 5, divided by 2 is 2.5 meters. So to find now, we're going to find the force coming this way. Density, gravity, area, y dash. So there's my density, there's my gravity, there's my area, and there's my y dash. Whack them in. 9.81 times by 7.5 times by 2.5 gives me all of that. Press that. 187 blah 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 blah. Press ENG. 187.62 kilonewtons. So the water is producing a force of 187 kilonewtons this way. And obviously the gate has got to provide a force, right, equal and opposite. So one's going that way and one's got to be going that way. Every force has an equal and opposite reaction. So for this wall to stay up, there's a force got to be coming that way to counteract that. So all I've said there is the gate needs to provide 187 kilonewtons to the right, because the water is providing a force to the left, to the left, to the left, and the gate needs to counteract that by providing a force, a reaction, same amount, to the right, to keep this in balance. So it's just another way of adding a bit on. And then the moment the gate needs to provide again, so all I'm going to do now is, like we did before, work out the moment. We'll work out the pressure the center of pressure, work out the moment about this base. So there'll be an anti-clockwise moment going this way, and then this moment on the other side has got to counteract it by going that way. So the moment produced by the water, say, is going to be going anti-clockwise, and to compensate for that and keep everything in balance, this wall or this gate has got to provide a reaction of a clockwise moment. So we know the force 187, and we're going to work out this distance here now, which is going to be this. So h dash is going to be coming down, which we know is 2 times the depth over 3. So we know that 2 times 5, 10, obviously divide that by 3 gives you that. Shouldn't have to do that in a calculator. So this force now, the pressure at the center of pressure is 3.33 meters down, like that. So that's our h dash by there. So the center of pressure is 3.3 meters down, and then from there down to the bottom is going to be 5, obviously. Yep, 5. Take away 3.33, which gives you 1.67. So the moment produced by this force about this point is going to be that force times by this distance. That's the moment going anti-clockwise. So the moment's going to be the force times by 1.67. So the force is 187 kilonewtons. Yep. So 187.62 kilonewtons times by 1.67, because there's the force, here's the distance. Bang. 313325.4 newtons per meter anti-clockwise, because that force is trying to tilt it that way. Press ENG, don't like that. So 313. I've gone 3.3. Look, kilonewtons per meter. So the water is trying to make this dam wall turn that way, about that pivot point, clockwise, because I'm calling this way clockwise, which means the gate and whatever is here has got to provide an equal but opposite moment to balance it all out. So you need to have a moment equal going that way. So it's got to be clockwise, because this one's going anti-clockwise. So to keep this wall or this sluice gate upright, you need a moment of that and a force of that. Now obviously if you watch these construction talking about dams, the dams are moving all the time. So that Richard Hammond one, if you watch it, it's quite interesting, because the dam is moving and they curve the dam. The dams are curved, so that force and that pressure is pushing the dam into the wall, into the mountain it's built on. So if you ever get a chance to watch that Richard Hammond one, I think it's called Big, because he did loads on like the biggest plane and the biggest oil rig, but there was one on about this massive dam, which does touch on a bit of what we've talked about here. So that's number 4. No, that was number 3. So number 4. Now the gate or a dam wall or something like a sluice gate is shown below the depth of the water behind the gate. So we've got both sides now. 10 meters behind it. So here's the water. And the depth in front of it is 4. So it's got 10 this side and 4 this side. The breadth of the gate is 15, so this is 15. Take the density of seawater to be 1030. So we need to find the resultant force and the resultant turning moment. So what's happening here is obviously this amount of water is going to have a force going this way. We'll work that out. And this lesser amount of water is also going to have a force going this way. So one's going to win. So the resultant force probably going to be going this way because there's more water here. So we'll work this one out, find the net. So it's going to be this one. So the force would be going this way, and then work out the moment. So, and then the moment about the pivot point there, because we've done the base of the gate. So there was a force left, so there's going to be a force going left due to this amount of water, this 4 meters. There's also going to be a force here going this way due to the 10 meters of water. And the resultant would be the net. So whatever that force there is, take away whatever this force here is, will give us the net. Now obviously, this force here, so this wall now has got to cope with all of these forces, so it gets a bit more hard now if we're going to design a dam. But we'll assume a couple of things, so make it easy for us. So the resultant force will be the net of both forces. So I'm going to work out the force due to the 4 meters. So here's our formula. Density, gravity, the area is going to be 4, because we're doing the 4 meters, times by this. So 4 times by 15 is 60 square meters, and this y dash is going to be that divided by 2, which gives us 2. So the force coming this way due to the 4 meters of water is going to be all of this. Density, gravity, area, and y dash. 1030 times 9.81 times by 60 times by 1212516 newtons. Press A and G if you want to. So 1.213 meganewtons of force going that way. So that force is going that way. And now the force we need to work out is the force going this way, which can be the same formula, just we're going to have a different y dash now. So the force due to the 10, same formula, same density, same gravity. Okay, so now we've got the area now is going to be 10 times by 15, because we've got 10 meters of water now and 15 length of the dam or the sluice gate, whatever it is. So 10 times by 15 in my book is 150. Y dash now is going to be half of this 10, which is 5. And then we can just stick it in the formula like we've done. So there's my density, there's my gravity, there's my area, and there's my 5. So 1030 times by 9.81 times by 150 times by 5, press equals 7578225 newtons of force, press E and G. 7.58, I've got to look, meganewtons to the right, which means we've got that much of force coming this way, 7.5 meganewtons coming this way, and we've got 1.2 meganewtons going that way. So the net force is going to be 7.5 meganewtons coming that way, 1.213 meganewtons more units coming that way. So the resultant force or the net force is going to be that, take away that, because we've got one force going that way, one force going that way. The resultant force is going to be obviously coming to the right, 7.58 take away 1.213. Don't forget the mega, 6.36 meganewtons to the right, because that is bigger than that. So you can have a force of 6.367 meganewtons coming here. So that's the resultant force on the gate. Now we need to know the resultant moment due to that resultant force. So that's just going to be using this force now on this depth. So we know the turning moment about the base due to the resultant force. So we'll just use it now as a normal example we've done previously. So H dash is going to be the center of pressure where this force we'll assume is going to act. 2 times d over 3. We know the depth is 10. So 2 times 10 equals that, divided by 3. 6.67 meters down. So we know this force acts 6.67 meters down. Center of pressure is 6.67 meters down from the top. We need to do the moment about this point. So the moment, the resultant moment is going to be clockwise. Obviously this force here will also have a clockwise, an anti-clockwise moment, but this is going to be the biggest moment. So force times distance, there's the force, and this distance here is going to be 10, take away all of that, which gives you 3.33. So because we've got a 10 depth of water, this force here is 6.671 down. So this distance in here, in green, is going to be 10, take away 6.67 equals obviously that, 3.33. So the moment due to that force about this point is going to be that force, which is the resultant force, which is 6.367 mega, times by 3.33 really. So 6.3676 take away 10 take away 6.67, close the bracket, should give me 636. What have I done? What have I done? Start again. 6.367 times 10 to the 6. You will work. Nope. All of that. Times. Did I do times? I don't know. Times by 10. Take away 6.67. 212. 212.02110 Newton meters. Press ENG. 21.2. Look, meganewtons clockwise. Newtons per meter, sorry. 21.2 meganewtons per meter clockwise. So the turning moment about that point is 21.2 meganewtons clockwise. Now obviously this dam wall or whatever it is has got to be designed and built and checked to make sure it can withstand all of these forces, which is where the skill in building a dam is, if anybody is ever going to get into building dams. So that's just a couple of questions on submerged surfaces. I've gone down the route of like a sluice gate and a dam, but you can apply this to oil tanks and gas tanks and, you know, moments on access points and pivots on, I don't know, if you've got a gate and it's got a pivot point there and a hinge, you know, things like that. So hopefully that makes a bit of sense. Any problems, let me know, and go and watch the Dam Busters. Over and